Okay, in this chapter we're going to look at some applications involving acids and bases, more specifically titrations, and also we're going to carry our study of solubility a little bit farther and incorporate the effects of pH in that. Okay, common ion effect, just to review, that's where we have a shift in equilibrium because we have an ion present in our solution that is also a part of our equilibrium. So for example, if we're looking at a solubility, here we have silver chloride, and if we add sodium chloride, since the sodium chloride is going to add a common ion to the solution, it's going to shift the reaction back to the left, meaning that the silver chloride will be less soluble than it was if we were, say, dissolving it in just pure water. Okay, what we're going to look at that's related to those are buffer solutions. Buffer solutions are where we have a weak acid and a salt with its conjugate base, or a weak base and a salt with its conjugate acid. Okay, we have to have both of those, and basically the benefit of these is that they are able to resist changes in pH from both directions. In other words, if we can add a base to the solution and it will adjust but not have a huge change in its pH, or we could add an acid to that same one, and again it will resist a huge change in the pH. Okay, so for example, here we've got acetic acid and sodium acetate, and so we have a buffer solution here, and say we add a strong acid. Well, that strong acid is going to react with the acetate, that's the base in this buffer, and the product will be the acetic acid again. Or if we add a strong base, then that base is going to interact with the acetic acid and make the acetate ion. Okay, so here's kind of just an example, and we're going to look a little bit later at some actual quantitative calculations, but here we have a buffer solution, and this particular combination would give us a solution that had a pH of 4.74. If we added some sodium hydroxide, a strong base, to this solution, we would just get a very slight increase in the pH. Alright, so let's look at these. Here we have some buffer systems, potassium fluoride and hydrogen fluoride. We have the weak acid, and the fluoride is its conjugate base. So yes, that would create a buffer solution. Then the mixture B, potassium bromide and hydrogen bromide. Hydrogen bromide is a strong acid, so it would not be a buffer solution. It has to be a weak acid or a weak base. And then we have sodium carbonate and sodium bicarbonate. And here we have our sodium is just a spectator, but we have the carbonate, it's going to be our weak base, and then the bicarbonate ion would be the conjugate acid, so that would indeed also form a buffer solution. Okay, Henderson-Hasselbalch. Basically, this is a way where we have a buffer solution, where we have weak acid and a salt with its conjugate base, or a weak base and a salt with its conjugate acid. This is a quick way to determine what the pH of that solution would be. You can still use an ice calculation for this, but this is just a quicker way to do it. Okay, so let's take a look at this. So I'm going to show it both ways. All right, so say here we have formic acid and sodium formate forming our buffer solution. Okay, so let's just take a look. All right, let's see. And I'm just going to use the dissociation of the formic acid. All right, I'm going to use that equation here. So we would get Okay, and so if we did an ice calculation with this, we would get, let's see, we have 0.3 molar here, and 0 and 0.52 molar there. Okay, so minus x plus x plus x, 0.3 minus x, x and 0.52 plus x, and so our Ka is going to equal, and we're going to make the assumption again that this is approximately 0 and that is approximately 0, so we would get 0.52x over 0.3 is our Ka, and for formic acid, let's see, I'll look it up in the book here. Formic acid, it is 1.8 times 10 to the minus 4. Okay, and so that would give us, let's see, and so I get an x of 1.04 times 10 to the minus 4. That's our hydronium concentration. So the pH then would be 3.98. Okay, so let's look at Henderson-Hasselbalch and see if we get the same value. So negative log, or the pKa would be the negative log of 1.8 times 10 to the minus 4 plus the log of base over acid. So our base was 0.52 and our acid is 0.30. So what does that give us there? 8. That plus log of 0.52 divided by 0.3. Let me go back and double check that. .8. Oh, I know what I did. Okay, let's see. So I have there we go, 3.98. Okay, so we get the same value whether we do the ice calculation like we've been doing or we use the Henderson-Hasselbalch. And the key thing to remember is that you can only use Henderson-Hasselbalch when you have both parts of the buffer solution present. Okay? Okay. Did I miss one? No, I didn't. Okay. All right. Okay, so let's look at a couple of characteristics of buffer solutions. All right, this is kind of what we had talked about before. So we're going to have a reaction. If I add a base, it's going to react with the weak acid. If I add an acid, it's going to react with the weak base. Okay, and again, we can use Henderson-Hasselbalch as long as we have both parts of the buffer solution present. Okay, here we're going to look at our initial buffer solution. So we can use Henderson-Hasselbalch, and so let's see. Our KB for ammonia is showing you where I'm getting these numbers. Is 10 to the minus 5th. So the Ka for the ammonium is going to be 5.56 times 10 to the minus 10th. And so let's see. So we have the pH of our solution is the negative log 1.8 times 10 to the minus 5th plus the log. The base is 0.3 over 0.36, our acid. So our pH, before we've done anything, is, let's see, minus log 1.8 to the minus 5th plus the log 0.3 divided by 0.36. So I get a 4.67 for the pH. Now let's look at after we have added 20 milliliters of 0.50 molar sodium hydroxide. Okay, so the first thing we need to do is you want to take care of the actual reaction that's occurring. So we're adding a base, so it's going to react with the ammonium ion, and it's the hydroxide that's going to react with it. So we're going to get ammonia and water as a result of that. All right, now we're going to do something, we're going to call it a BCA, just to distinguish it from an ice, because these are going to be in moles. This is where we're doing the stoichiometry of the reaction. So we're going to look at here, I have 80 milliliters of my buffer solution, so 0.08 times 0.3. So I have 0.024 moles of the ammonia and 0.08 times 0.36. I have 0.0288 moles of the ammonium and then 0.02 times 0.05. I'm adding 0.001 moles of my hydroxide from the sodium hydroxide. Okay, so now the change is going to be based on the limiting reactant. Limiting reactant is going to be consumed. These are 1-to-1, so my limiting reactant is the hydroxide in this case. So my change line is going to be based on the stoichiometry of the reaction. All right. And the after, this is before, change after. After is going to be 0.0278 and 0.025. Okay, we are now, let's see, we've had 80 mils plus, so we now have 100 mils. So my ammonium, or my acid concentration, is 0.0278 moles in 0.1 liters. And the ammonia is 0.025 moles per 0.100 liters. So that would give me 0.278 and 0.25 molarity. So my pH is the negative log of 5.56 times 10 to the minus 10th, and the log of 0.25 over 0.278. Okay, so that's going to give us plus log . I'm getting 9 Oh, okay, hold on. Now, that just showed me I made a mistake up here because I used the KB instead of KA. And this one, yeah, should not have such a huge jump in the pH there. So let's try that again. Yeah, all right, so without adding anything, all right, so originally, there we go, 9.18 was the original one, and so adding some of the base, we would expect it to go up, which it did, but not by very much. Okay. All right, new term here, the capacity of a buffer. That represents how much can it neutralize of added acid or base. So here we have, let's compare, we have two buffer solutions. They have the same components, all right, just in different concentrations. However, it's still in a 1-to-1 ratio of the weak acid to its conjugate base in both cases. It's just the actual amount of each present is different. So these buffer solutions, because the ratio, remember the buffer solution, Henderson-Hasselbalch, the thing that changes is that ratio of the base to the acid. So if this ratio is the same, like it is in these two buffer solutions, then it's going to buffer to the same pH. However, the amount is going to determine how much of an acid or base could be added to this buffer and still have it buffer or limit the change in pH. That's going to be based on the amount that's present of each of the parts of the buffer. So that's the capacity. So our capacity would be different in these two solutions, even though they would be buffering to the same pH.